Hello students, for the last lecture we have to give some examples of a group. Now we have to, in this lecture we also discuss some more examples of a group. Let us begin with the example of a set of m by n matrix over the real numbers under the user matrix additions, and this is form is a group. So let A and B belongs to the m by n matrix over the elements of a R. So we denoting A is the form of a this A of ij, and B we denoted as a B of ij. These are the m by n matrices are there. So because under addition we can say that A plus B is same is written as A of ij plus B of ij, and that is the same as we can say that A of ij plus B of ij, and then you know that this is all are Aij are the belongs to the R, Bij also the belongs to the R. So Aij plus Bij whole thing is belongs to the R. This complete elements of this is R. So this means this is a matrix, again is a m by n matrix over R. So this set is belongs to the m of R. So in generally we can say that this A plus B is the element of a m of n by n matrices R. So this matrix set is clearly is closed under the addition. Now similarly we can say that matrix addition is clearly is associative. Now we have to find the set if there is exists a identity element or not. First, suppose 0 is a 0 matrix, we can say that, and this belongs to the M of set of real. Now this is the 0 matrix. If 0 plus A, we can say right is a 0. 0 matrix, all the elements of this is 0. This can be written in the form of a 0 plus Aij, and then you can say that clearly this can be written as A of ij, and this is equal to A is there simply. Similarly, in another way we can say that A plus 0 matrix we can write in the form of A of ij plus 0, and this is again is A of ij, and this is again A. So 0 matrix is called the identity matrix of identity element of this set. Next we have to check is the inverses exist or not. So I just say that simply suppose like this we have to, and straightforward we can verify this is a commutative condition of a matrix addition is associative and commutative, and that is a 0 matrix is satisfied into this A plus 0 is equal to this. So Aij is equal to this satisfy in this condition. Now we have to find the inverse is this. So minus A, if A is equal to this, we can say that minus A is equal to, you have a minus times Aij. So if A plus minus A can be written in the form of A of ij plus minus Aij, this is equal to, you have a Aij minus Aij, and this is giving you a 0 matrix is there. This is giving the identity element. This means if we have A is the element of a this matrix, then minus A is also belongs to the this same m by n matrix. So we can say that A plus minus A is equal to giving the identity element, the 0 matrix is giving. So in this case we give X inverses also exists. So we say that this MNR is under addition matrix addition is form an abelian group. Now we have to think about what we can say about if a this set MNR n by n matrix set of a real number under matrix multiplication is form a group or not. But matrix addition, because we can know that matrix multiplication under is a closed, is not a problem. We have a identity elements is a identity matrix is the identity elements. So but not every element has a inverse, the 0 matrix does not have a inverse in this case. So if under multiplication this matrix m by n matrix over a set of elements are a real numbers, is not form a group, because inverse properties fail, because 0 matrix has no inverse exists in this, is undefined from this, in this case is equal to this. So now under what condition we have to imposing this, means under multiplication is such a matrix is form a group. So we have to say we take a matrix like this group under what condition we have to impose in the matrix. That means we have a matrix under multiplication form a group is there. So we take a all set of all n by n invertible matrices we define in this form. GLNR A is the determinant of A is not equal to 0, and that means this form this GLNR under the usual matrix multiplication form a group, and we have to easily say that because determinant of A is not equal to 0, so this set is clearly is a closed. We have to show, because matrix multiplication is associative. So under this all matrix GLNR also matrix multiplication is associative. We have to have a determinant of identity matrix is the identity matrix we have a. So we have to just take a determinant like A and B. First we show that is a closeness AB belongs to the GLNR. So if A and B are the element of this G, we can say that determinant of A is clearly is not equal to 0, and also determinant of a B is also not equal to 0. Then you know that the property determinant of A B, by the property of a determinant we can say that determinant of A into determinant of a B, and determinant of A is not equal to 0, determinant of a B is also not equal to 0. So we can say simply that this product is also not equal to 0. If it is this is not equal to 0, then we can say that determinant of AB is not equal to 0. If determinant of AB is not equal to 0, that means we have to say that this A and B are the element of a GLNR. So means this AB is if we take arbitrary element A and B are the element of a GLR, and then we can show that A and B again satisfy condition into GLNR, means this is closed under the matrix multiplication is there. And next we have to check, because matrix multiplication is associative, so we have no need to verify that matrix multiplication is associative is there. Next we have to check that if this matrix of under what is the identity elements of a this set is there. So we take any identity matrix I n by n matrix, we have to take any identity matrix, and A is the element of a GLNR. So we can say that identity matrix into A is again A, and this is same as a, we can say that A into identity matrix of this thing. So clearly identity matrix of a determinant of a identity matrix is clearly is not equal to 0. So In is the element of a GLNR, and we have to say that the identity matrix of this set is an as working as a identity of this set is identity. So the identity matrix is the identity of this group. So this satisfies this identity also. For you can say that identity matrix is the identity of this, because determinant of identity matrix is clearly is not equal to 0. And now we have to check the, because this is all the matrices are invertible, every element has its inverse is exists there. If A belongs to this determinant of a node is equal to 0, we have to set if all invertible matrices are there. If A is the element of a GLNR, then clearly A inverse also belongs to the GLNR. So if we take A inverse, then we have a clearly identity matrix, we have also A inverse, A is also. So if A is the element of this, then GLN also the element of this. If we have A inverse giving the identity element, A inverse A is also giving the identity element. So we can simply say that every element has an inverse is also exists. So we can say simply this is form a group under multiplications, usual multiplication, matrix multiplication under this. But this for a this we can close net, we say again we have to show that close net other way also we can prove that is a close net. We use the property of this inverse property AB inverse. We use the uh, associativity conditions here, and then we have this is identity element, and then we have to identity. Similarly, if we have to writing this as also identity, so this is giving, this means we have to show that AB is equal to this. So we have to show that B inverse A inverse is equal to identity, and also we have to show that B inverse A inverse AB is equal to identity. By the definition of identity, we can say that this means AB is a invertible. So AB is invertible as well. So we can say that JNS is a closed under multiplication. There is a two way we can prove this set is a closed under by the determinant property of determinant also, and by the property of a inverse also. So this is clearly we have to, this means we can say that GL and R indeed a group, and this group is called the general linear group over the reals. Now this group is clearly is a non, because we know that the generally matrix multiplication is not commutative. So this is also is a clearly how a group is a non-abelian. For example, we take a n is equal to 2, we have a two invertible matrices. I take a this one and this one, because both of them is a determinant of a this and determinant of a this, both are non-zero. So we can say that these are this, but if we take a product of a these two from this side is giving 2 1 1, but is the product of a this side, we have to just say that 1 1 2. So this means these all are these positions are different. So we can say that clearly A and B are not the same. So we say that this group is not an abelian group. So this is the example of a non-abelian group, and now we have to take a special case of a this group. Suppose we take a, in place of a determinant is not equal to 0, we just write determinant of A is equal to 1 for all n by n matrices having the determinant 1, is again this is a non-abelian group under the operation of a matrix multiplication. Clearly matrix under this case, this is a closed because determinant of A is equal to 1, we take a determinant of A and B. So if we have A and B are the element of a SL and R, clearly if SL and R, that means determinant of A clearly is equal to 1 and determinant of a B is also equal to 1. If we choose the property of a determinant, AB is equal to determinant of A into determinant of a B, and that is equal to, you have a 1 into 1 is equal to 1. So if determinant of AB is also 1, so this means we can say that AB is the element of a S, L and R. So if SL and R, so this we can say that clearly this this set is a closed under the matrix multiplications. So this is clearly this is the special case of the previous example. So that's why we can say this is a special linear group, and this is also is a non-abelian. I just proved the, because determinant inverse also properties hold. Trivially we can say that, I just say that this is a non-abelian. I take a two matrix A and B where the determinant of a is equal to 1, determinant of a B is equal to 1. When product A and B is equal to, we have a take a product of these two, we have this matrix. If we have take a product of B into A is equal to this matrix, and then clearly these two are the different. So we show that A dot B is not equal to B dot A. So this is a special group of a special case in the general linear group where we take a determinant of A is not equal to 0, but in this case we have to taking the determinant of A is equal to 1. So is a special case, so that's why we can show call this is a special linear group is there. Now we have a next example is this. We take a let G is equal to A alpha, and we have to take a cos alpha minus sin alpha, cos alpha, where alpha is a real number. The operation of a matrix is a group. So operation of matrix multiplication, this is a, we have to show that is a group. Now you see this example is very interesting example. If you see if you find the determinant of a alpha, you getting is equal to 1. So this is the special example we have to, this previous example you just see this one. So if there is a case is a determinant of A is equal to 1, here also we have to take a matrix, such a matrix where this set, clearly we can say that if we calculate determinant of this, you just see we can say that if determinant of A alpha we can write is equal to cos square alpha plus sin square alpha is equal to 1. So clearly determinant of A alpha is equal to 1. So that is the special case of the previous example. This is a special linear group. Now we have to show that this special linear group is to satisfy the conditions of all the properties of a group. First of all, we have to satisfy this, means this is a under multiplication of a matrix is a closed. So we take a two matrices A alpha and A alpha and A beta belongs to the G. Now we take A alpha and A beta. This is cos alpha minus sin alpha, cos alpha, and cos beta, sin minus sin beta. We take a product of these two, then you have a use the clearly this is a cos alpha cos beta minus sin alpha sin beta, and then we have to multiply it by this minus times cos alpha sin beta plus sin alpha cos beta, and also here sin alpha cos beta plus cos alpha this. And now you see this one clearly, this is cos of alpha minus alpha plus beta, and then we have to we have to clearly, and then you have a minus sine of alpha plus beta, then you have a we have a sine of alpha plus beta, and then you have a cos of alpha plus beta. So this means this we can write this accordingly, this can be write into A alpha plus beta, but alpha and beta, alpha is a real number and beta is also is a real number, then alpha plus beta is also is a real number. So we can say simply is that alpha plus beta is also belong to R. If alpha plus beta belongs to R, then A of alpha plus beta is the element of a G. So if A of alpha plus this set is the element of a this set G, if this is G, that means this whole A alpha A beta is also the element of a G. So we can say that simply is this set is a closed under the matrix multiplication is there. Associativity, we can say that clearly A alpha, A beta and A gamma are three elements of a G. Then we have to A alpha, A beta, A gamma. Then A alpha, A beta, we have to just say that can write written in the form of A of alpha plus beta and A gamma, and then we can write is A of A alpha plus beta plus gamma, and that A alpha plus this is A alpha beta gamma are the real numbers, and the real number this under addition satisfy the associativity conditions. So we can write A of alpha plus beta plus gamma, and then we have to write by the property of A alpha plus beta, so A alpha A of beta plus gamma, and then we have to just say that A alpha and A of beta plus gamma can be written in the form of A beta A gamma. So associativity condition is hold also in this case. Now we have to find the is existence of inverse is there or not. So we have to take A0 where alpha is equal to 0. So we have clearly cos 0 minus sin 0, cos sin 0, and cos 0 is equal to 1, 0, 1, 1, and that is satisfy this. This is the case of this. So A0 is a matrix is such that identity matrix, and now in this you see where in the SL and R, we have to say that the identity element of this matrix is identity. So this is clearly again cos 0 minus sin 0, this is giving you the identity matrix. So A0 belongs to the G clearly, is the identity of a G. Then A0, A alpha can be written as a of 0 plus alpha, and this is 0 plus alpha, L is a real number, so A alpha, and this can be A alpha plus 0, so this is clear. So A0 means is the such a matrix where the cos 0 minus sin 0, sin 0, and we can say that is a clearly is a cos 0 is satisfy this condition. Now we have to find the existence of a inverse of this problem. So we have to see, let A alpha is the element of a G, then I just write in the form of this A alpha is this cos alpha, and sin alpha minus sin alpha cos alpha is such a matrix. This can be written in the form of cos of minus alpha minus times sin of minus alpha, and this is sin of minus alpha, and then we can write the cos of minus alpha. And now this is the matrix is giving you a clearly, this is cos of minus alpha is the cos alpha minus sin of minus alpha, and this is the nothing but is equal to, in place of alpha, if we replace is a minus alpha into the our set G, so we can say that A of minus alpha, and if we take A alpha, A of minus alpha can be written as A of alpha plus A of minus alpha, and alpha is belongs to the R, minus alpha is also the element of a R, and this is giving to the 0 A0, and similarly we can say that A of minus alpha plus alpha is also giving you a A of minus alpha into A of alpha is there. So if A alpha is the element G, then A of minus alpha is the called the inverse of a this element is this. Now we have to show that this is a clearly is an abelian. If we set A of alpha, A of beta can be written as A of alpha plus beta, and now you see alpha and beta are the real number, and the alpha beta is a real number, then the under addition these two real numbers are commutative. So we can say that beta A beta plus alpha, and then this should be giving you A of beta, A of alpha. So clearly since alpha beta are there, so G is abelian. So this G under this G this group under multiplications we can say simply is this is a clearly is a form an abelian group is this. So now think this is a very special case of a SL2R. SL2R is not a abelian group, but there is some special case is this. We find that this is form an abelian group if we have to take a matrix of a special types is there. Another example we have to just move to the further, we have to take let G be a set of all non-zero real numbers and define for AB belongs to the G, A composition B is A square B. My question is this, is G under this binary operation is a group? Okay, that means we have to check is this group or not, because A and B are the element of a G. So A is non-zero and B is non-zero real number, then A square is again is non-zero, B square is also non-equal to 0. So this means we can say that simply is this A square into B is clearly is not equal to 0. If it is not equal to 0, then we can say that A composition B are the element of a G. Means this is a closed under this binary operation. And also associativity we have to check is this, so certainly G is a closed under this binary operation, we have to say that. Interesting thing is this is associative or not. So let us try, we have to check if this set is associative or not. So first we have to starting from we have to satisfy this condition. We have to just check A star B star C is the same as A star B star C. That is, we have to just say A star B, we have to just say that A square we have to apply into this set. So this means A star B whole square into C, and then we have to say that this side we have to applying this, so A square into B composition C, and this also we have to say that in the form of, if apply the definition into this set, so A square B ka whole square into C, and in this case a square, b square, c, and now which boils down to only possibility a square is equal to 1. This is true only in the case a square is equal to 1, and which is hold only the case when only for a is equal to plus minus 1. So in general, the associativity law does not hold uh, in G relative to this binary operation. This is true only for, because there is a is, we have to either a is equal to plus 1 or minus 1. So this is not a group. We can similarly verify that even G does not have an identity element. We cannot find any element which can be proving that a composition E. Like this, we can say that we have not find any element of E is equal to written as a square E, and this is giving you a square. So we cannot find such elements of a non-zero element which is giving you a square a is equal to identity element of this thing. So we have to find such a element. If we have to, we can easily, where G does not have as an identity element, and even to discuss the inverse relative to the star binary of star would not make a sense. So G under this binary operation clearly is not a group is there. Okay, now we have to very interesting example is this. Again, set of a natural number we have to taking, and P of n be the power set we have to taking. My question is this: is this power set under the operation is a union, is a group or not? So clearly we can say that if we have a power set, this is clearly is closed under the operation of a union. We have to simply say that A and B are the two elements of this power set. Then A is the containing n, and B is this. So A union B is also containing into the natural number. Thus A union B is the element of a, again is a power set of this P of this Pn is there. And also is a power set under union is associative, are there a set of union is also associative. A union B union C is the same as A union B union C. Next is, what is the identity elements of this group? We have to verify what is the identity element of a this set. So we have to take this means if we take a union, if we take an empty set, is the this thing belongs to the power set is this. So A is the element. If we take a union of any element of this empty set is giving the set itself. So you can say that this is a union of A also. So phi this empty set is an identity element of this group. So we have to say the closure property is satisfied, associativity property is satisfied, identity is there. What about the inverse of this? So inverse of this we have to try. Is the inverse of this set is exists? Inverse in this case is it does not exist. We cannot find any element A inverse belongs to the power set of this. A union A inverse giving you the empty. A union A inverse, we cannot find any element. We take a union of this set is giving you empty set is there. So clearly inverse of this, you take any element, you can take any element 1 or 2, take a union of this giving you the another set is there. Is not giving the, never you giving the empty set is there. If you take a union of A union empty set is giving you A, and then clearly we have to just say that P power set of a natural number over binary operation is a union is not form a group into this thing. What happen if we have to change the binary operation in place of a union? We take a intersection is this. Is this in this case is this is a group? So again trivially we have to say that is a clearly is a closed. A and B belongs to the power set, and then A intersection B again this. The A intersection B is the again is you take any two elements of this power set, take intersection is again going to this set is there. So is clearly closed and also associative, because intersection A intersection B intersection C is the same as the A intersection B intersection C. So another set of intersection is also satisfy the this set. And if we take a any elements of a set, n is the subset of a n, so n is the this thing. If we take a intersection of n, so whole set n set of natural number we take. If we take a set of natural number, take any element of this set, a intersection natural number is giving you a is there clearly. So we can say simply is that the whole set n is the working as a identity element. So set of natural number in this situation, we have a set of natural number as an identity element. So we can say simply is a whole set is identity element. So we have to closure properties hold, associativity properties hold, and now we have to show that the identities also exist. The whole set is an identity element of this under the binary operation intersection of this power set. Now, what is the inverse of about the inverse of this? Again, inverse does not exist in this case. We cannot find any element A inverse belongs to this. We take intersection of this giving the whole set. You take any set, whatever this intersection, if you take intersection of any two sets, is not giving you to the whole set n is there. So in a power set, we have to take a two different element, take an intersection of these two is never giving you the whole set n is there. So with this case, this situations, we can simply say that the power set of natural number operation of intersection is not a group. So we have to show that clearly this power set of natural number under union binary operation and under intersection is a binary operation is not form a group is there. Now let us try some different types of example of binary operation. For a group, we have to just say that let star be a binary operation on Q set of all positive rational number, and the operation is defined as A star B is equal to AB by 2. Then we have to question is to show that this set of rational number under addition over this binary operation is an abelian group. So we have to try if this is abelian group satisfy this condition or not. So we have a clearly we have to A and B are the element of a Q positive, and we have defined A star B is equal to AB by 2. A is a positive rational number, B is a positive rational number. If we take a multiplied of these two positive rational number is again is a positive rational, this belongs to the Q positive, and if divide by 2, then this whole thing is also belongs to the Q positive. So if this whole thing, if we have to just say that this whole thing is belong to the Q positive, so if this is Q positive, then we can say that simply is A star B is also belongs to the Q positive is there. So we have to just say that is satisfy the condition of A star B is also belongs to the Q positive. So this is simply we say that under the binary operation this is a closed. We check the associativity is there, take A, B and C are the element of a Q positive. So we take A composition, B composition, C, and we can say that simply A composition, B composition, C, A composition, and then we have a BC by 2, and this can be written as A of BC by 4. If we have to just say that this is simply this A composition B composition C can be written in the form of a AB by 2 composition C, we can say that again ABC by 4. So these two are the equal, we can say that is satisfy the associativity condition is satisfied in this case. Now what is the we just say that is a existence of a identity of a, in this case we have a. So let E be the identity element for the moment we have a. So we can say that E is the identity element, E composition B by the definition is this A E by 2. By the property this should be is equal to A is so this can be written in the form of a E is equal to 2A, and we have to A is a positive real number, so we have to simply say that E is equal to, we have a 2 is there. So there is an element A, we have to take a composition of a 2 is equal to A, 2 by 2, so this is equal to A. So E is equal to 2 is the identity element in this case. So 2 is the identity element of in this key. So clearly we can say that this identity element is exists, and a identity element is equal to 2 in this case is there. Now we find the inverse of this. What is the inverse of this in this case? So we have to cite a composition b is equal to identity is equal to 2. By the definition ab by 2 is equal to, we have a 2. So we can say that simply is equal to, we have to just say that b is equal to 4 by a, because a is a positive rational number. So we can divide this as a clearly. So if a is the element of this, then inverse of a is 4 by a. So we have to take a composition is 4 by a is equal to, you have a simply say that uh, a, a into 4 by a by 2, and then clearly is equal to, you have to just say that is equal to 2. So we have to just say that is identity element satisfies this condition. So we say that every element, if a is the element of a q positive, then 4 by a is the 4 by a is the identity element of a inverse of a this set. So we can say that every element has an inverse is there. This satisfies all the properties of groups or groups. Now we check if this is an abelian group. So we have to say that a composition b is equal to a ab by 2, but a and b are the positive rational number, and the rational number under multiplication is a commutative. This can be written as a ba by 2, and this can be written as a b composition a is there. So now I just say that under this operation we have to say this is a clearly this q positive under the binary operation. We have defined this operation is a clearly is an abelian group. So I think you have just very various examples I will show that, and then groups. I think you have to understanding the groups with the examples. In the next class we have to continue the some modulo applications, things you know the addition modulo of a group under whatever conditions. So we have to take a modulo and into the continue into the next lecture. So I will stop here and continue for next lecture for congruent modulo of form a group under the addition, and under what condition is a group for multiplication is there. Thank you very much.